So this new section is about function composition and invertible function. So let's see the definition of composition. Here you have two functions, f with domain A and codomain B and g with domain B and codomain C. It's important that the codomain of f be equal to the domain of g so that you can form the composition of f and g. Then the composition of f and g denoted by this notation, and you read it like this: g circle f is the function g circle f whose domain is A and codomain is C. You can remember it like this: first we go from A to B and then from B to C. So we ultimately go from A to C, and the function is defined like this: g circle f of x is by definition g of f of x. Let us see if it makes sense. So what we are saying is that the domain of this new function is A. So you choose an input x from A, which is an element of A. So applying the function g circle f on x means first you calculate f of x. Does it make sense to calculate f of x? Yes, because the moment you choose your x from A, that is also the domain of f. So f of x makes sense and it's an element of B. So f of x is an element of B and B is the domain of G. So you can calculate g of f of x. That also makes sense, and that will be an element of C. So ultimately we are getting an element of C. And to better understand this, you have this diagram where you can see the three sets A, B and C. So we start here at the element x in A and we apply the function f to it, obtaining the element f of x in B, and then to that we apply g. So finally we get g of f of x, and by definition the g circle f image of x is this element obtained in two steps. Note one more thing, that this really is a function. That means it assigns a unique element of C to every element of A. How so? You are choosing any element x in A. So for that x, there exists a unique element f of x in B, because f is well defined. And for that f of x in B, there exists a unique element in C which G is giving you, which is associated to f of x, and that is g of f of x. So for each element x in A, you are getting a unique element g of f of x in C. So yes, really this is a function, and this is said to be the composition of f and g. Let us next see this example. Here also we have two functions, but now two concrete functions. The first function f is from this set to this set, where the domain consists of these four numbers 2, 3, 4 and 5, and the codomain has 3, 4, 5 and 9. And the second function g has the domain which is equal to this codomain of f. You know, this condition should be true so that we can form the composition. And the codomain of g is 7, 11 and 15. And the functions are defined like this: f of 2 is 3, f of 3 is 4, and f of 4 and 5 are both equal to 5. So 9 is not an output of f. So you can see that this f is not on 2. And at the same time, because of this, f is not 1, 1. Not that we need to see those things here, but I am just simply saying. And g is defined like this: g of 3 and g of 4 are both equal to 7, and g of 5 and g of 9 are both equal to 11. So g is also neither 1, 1 nor on 2. We have to find g composition f. So we straight away calculate the values of this function at the inputs. Inputs means the points in its domain. Because the domain of this composition is the same as the domain of f, so you go back and look at the domain of f. There you have this point 2, and g circle f of 2 by definition is g of f of 2. Now your f of 2 is 3, so that equals g of 3, and g of 3 is 7. So that's how this is 7. That means this composition maps 2 onto 7. Note that 7 lies here, which is the codomain of G and also by definition the codomain of this composition. Next, we also have the point 3 in the domain of F and hence in the domain of this composition, and G circle F of 3 is by definition G of F of 3. Now F of 3 is 4, so G of 4 and G of 4 is 7. So the point 3 also gets mapped onto 7, and similarly you can see that G circle F of 4 is 11 and G circle F of 5 is also 11. We can draw a diagram to show all these things, an arrow diagram. And this is the arrow diagram of the situation. So the first set of arrows is for F and the second set of arrows is for G. So F maps 2 to 3, 3 to 4, 4 to 5 and 5 to 5. And G maps 3 to 7, 4 to 7, 5 to 11 and 9 to 11. So from here you can clearly see that in calculating G circle F of 2, first we go from 2 to 3 and then from 3 to 7. 2 to 3, 3 to 7. Then here from 3 to 4, 4 to 7. 3 to 4, 4 to 7. Then from 4 to 5, 5 to 11. 4 to 5, 5 to 11. And finally from 5 to 5, 5 to 11. 5 to 5, 5 to 11. This 9 getting mapped onto 11 by G plays no role, but that's not a problem. In this next example, we have again two functions f and g, and this time both of them map R into R. So in this special case, we can consider both these compositions, G circle F as well as F circle G. Both of them make sense now. And the functions are defined like this: f of x equals cos x, so it is our usual cosine function, and g of x is 3x squared, this quadratic polynomial function. And after calculating these compositions, we have to show that as functions they are different. So unlike for example product of numbers, say 2 times 3 which is equal to 3 times 2, you can think of composition as a kind of product, an operation. It does not have that property. It's not necessary that G composition F should be equal to F composition G even when both of them are defined. So the first thing we see about these compositions is that both of them map R into R, and that is pretty easy to see. What should be the domain of this composition G circle F? By definition it is the domain of F, which is R, and the codomain of this composition should be equal to the codomain of G, that is also R. And similarly the domain and codomain of F circle G are also both of them equal to R. Alright, so we take any point x in R and calculate G circle F of x. By definition that is G of F of x. But F of x is our cosine function, so G of cos x. But gx is 3x squared, so G of cos x is 3 cos square x. Whereas F composition G, if you similarly calculate, turns out to be cos 3x squared. So from the look of these functions itself, you can see that they are looking quite different. But of course, you need to give some concrete reason for why they are different. To show that they are different functions, we just have to show that they do not agree at some input. Let that input be 0. You may choose some other input also. I conveniently chose 0. So G circle F of 0 is 3 cos squared 0, and cos 0 is 1, so we get 3. But F circle G, according to this formula, is cosine of 3 times 0 squared, and here we get cos 0, which is 1. 1 is not equal to 3. So at 0 these two functions do not agree. So how can they be equal? They are different functions.